Up till now, we were covering deep ultraviolet. From now onwards, we will be talking more about more energetic energy sources, which is extreme UV or X-ray lithography, which can be soft or harder. There are also electron beam or focus ion beam based methods. So either we use electron beam or ion beam for writing on the surface or printing features. Then there are also some electron and projection lithography based methods, which has a higher throughput, but again there are some limitations which we'll cover. There are some serial methods, atomic force microscopy, scanning tunnel microscope, that will also go through, and soft lithography and nanoprinting. So I think we'll go through topic by topic. So, but if you look at the trend, how the lithography trend looks like. So there is a very well-known law. It's called the Tenants Law, and which correlates dimension or resolution and throughput. So basically, what it says that A and T, which is actually throughput of your system, like how much quickly you can have many features or how many wafers you can process in a time, how is that is related with your resolution of the system. So basically, when you print a smaller feature size, let's say 100, for example, 100 nanometer, you will get some throughput. But now if you make it half, let's say instead of 100, you get a 50 nanometer, so your throughput will significantly be reduced by power 5 ratio. So that's a challenge normally which we have in most of the cases. When we improve the resolution, let's say from optical lithography to atomic force lithography or electron beam based lithography, although you can have very nice resolution, but your throughput is actually significantly reduced, so that's a big problem. And the trend, you can also see it on this graph. This is the resolution or minimum feature size which you can print. So 10⁻�0 means 1, right? So 1 nanometer up to 1000 nanometers. And there are quite a few technologies which are out there. So let's say if we look at this one, it's called the scanning tunneling microscopy based lithography, where you can print features actually in less than a nanometer. Then you have E-beam, which falls in sub 10 nanometer range. With the E-beam, you can have this much resolution. And there are AFM, atomic force microscopy, Gaussian beam lithography, and quite a few other ones. What is this one? Optical step and repeat. So this is optical lithography, where you have actually very high throughput, but then your resolution is also not that great. So that's a general trend. So the question is, where on this graph, if I ask you to point on, to identify an area where we want our ideal technology to be. So whether, for example, our ideal technology should be here, which place it should be in this graph?
Depends on application.
Yeah, but we want a good resolution always, right? And we also want a high throughput. So it's kind of desired features. Bottom right. Okay. Anyone else? STM. Okay, so that's already, we already have ideal technology there, right? So maybe there's no room for improvement then. Yeah, it should be on the right corner here. So smallest resolution possible and highest throughput, which is not achievable, by the way, right now, but that's where we want it to be. So we want this graph actually to come over here. But that's what we are suffering nowadays so far. So how we can actually how we can achieve nanofabrication like a high resolution system, but with a higher speed, we can actually do the parallelization of the large areas. Instead of using one electron gun or one fabrication source or energy source, we can use multiple of them. So we can utilize parallelization principle. We can do fast writing with that. But again, Then there are issues with the cost, whether it's a cost compatible, whether it's a feasible also or not. And there are also issues with the alignment, how you align different sources together, especially when you are at a sub 10 nanometer range where structures are really, really small. So aligning your sources also will be challenging. But yes, there is a one way that you can, instead of writing one place, you can write multiple places, and if you align them, so there is a hope that you can improve the throughput of high resolution systems. So now let's go through all these one by one. Let's first look at the proximal X-ray lithography or extreme UV lithography. So extreme UV or vacuum UV is also sometimes called soft X-rays because they are also very energetic. The lambda is about 1 to 40 nanometer. In case of hard X-rays, the lambda is actually very small, less than 0.1 nanometer, and that's why it's very high energetic, very penetrating. Typical proximal X-rays beam has a lambda of 0.45 nanometer. That's also considered hard. So basically, you can say if it is more than 1 nanometer, it's called soft X-rays. If it is a 0.45 or smaller, it's called the hard X-rays. Okay, so those X-rays is kilo electron volts, very, very high energy. So you cannot really use the glass-based masks and all that with these high energetic beams. Now the question is, when we say X-rays, I thought, okay, so it's a good idea maybe to give you a little bit background about how X-rays are being produced. So it's very simple, but if you really want to build a system, that may be a little complicated. But in terms of a technology description, that's not hard. So basically, this is a one X-ray generator. You can consider that it's kind of a bulb, where you actually heat up a filament. It's a metal filament, and then you apply very high potential between this filament and this is your target. So you apply very high potential between this one and that one. So because this is electron source, so you would be applying a negative terminal here and positive on the other side. So you can push electrons to the other side, right? There will be air gap, so it's a vacuum. So basically, there is an air gap or vacuum gap. So if you apply low voltage, 100 volts, 200 volts, you will not see any electrons movement from here to here because it's the air, right? But if you apply very high voltage in kilovolts and the distance between these two electrodes is small, then you will start getting the electrons actually start jumping. You are really pushing them hard, so they start jumping from this filament to the other electrode because of high potential which you're applying. So they are bypassing the air barrier or vacuum barrier as at a high voltage. Are you guys familiar with the corona effect in a power transmission lines or power generation? So that effect is that when you have a 5000 kV line, okay, very high power line, and sometimes you see a spark in air, and that happens that you have very high potential, and the electrons, because of the humidity or certain environmental conditions, the electrons tries to flow through the air, and you see that lightning. And it's exactly similar. You apply very high voltage, electron likes to actually jump you bypass the air barrier or vacuum barrier. So in that way you can generate electrons from a filament, and definitely it has to be some compatible material, maybe not all. Let's say if you put a carbon, it may not be able to produce what you want. So it has to be mostly copper or some other metals which are normally used for this purpose. But yes, the goal is to have electrons, and then when electrons come and hit the surface of a second electrode, in this case we say it's a target material. They hit a surface, they transfer energy, and then the X-rays are produced. Okay, how X-rays are produced? We have to look briefly into the atomic structure of the atoms, electronic structure, and see how the X-rays are produced. Because X-rays are electromagnetic wave, like a light, and electrons are not really the EM wave. But electron also have a property of EM, but let's not go there. It will be more complicated. But let's stay simple, and let's look at how we can have electrons, X-rays being produced. For example, let's take an example of, let's say we have one atom. This is a nucleus. Let's make only 3, okay, to make it simple. So 3 outer shells, and we have these electrons, a few of them in outer shells. And as you know, the electrons which are at the outer shell, they have more energy, right? They are more energetic. And the ones which are in the inner shell, they are more stable generally, because they are close to your protons or nucleus, so they are bound with the nucleus with the more strength, electrostatic force. So but the outside ones are bound with the less potential, and then they can easily also release from the surface. Now, let's say if we have this material, and now we expose this material to electron gun or electron shower. A lot of electrons coming and hitting with the target, like what was happening in this our schematic. So what happens that when electrons come, so what electron will do? When it hits the surface, it will transfer their energy, right, based on how much energetic they are. They will transfer, they will hit maybe other electrons to kick them out. So when an electron comes, and let's say this is one electron, it comes and hits it, and it kicks it out from its core shell. Okay? So when it kicks it out, then this electron is called the secondary electron. And this is the incident electron, and this is secondary, which is being ejected, right, because of inelastic collisions. And then what happens? And this is the same, by the way, principle which is used to build the scanning electron microscope. In the scanning electron microscope, which is an electron exposure-based microscope, which has a very high resolution. So basically, what you do is you have a surface which you want to image, which can have nano features or whatever you want to image. You shower an electron with electron gun on a small area, and exactly the same way, and then those electrons will hit the electrons from the material, and there will be some secondary electrons being generated, and you have a detector there which detects only the secondary electrons which are being ejected from the material. So in certain area you will have more ejection. For example, if it's a high feature which is close to your gun, or lower feature, based on that you have a different electron ejection as the secondary electrons. And so with the gun you are accumulating basically small area where there is more electron being ejected or where is less electron being ejected. So after that you can actually build a contrast of the surface, and you can generate a pattern with some image processing. So that's how you can see, okay, the small features on the surface. And also you can characterize, the material shows a different contrast when, let's say you have a gold and you have a silicon dioxide. You'll have a more ejection from one or other based on the material properties, and then that can also give you a contrast to see how your surface looks like. So, but coming back to the X-ray, so you have an electron gun, you are shining on the surface, it transfers energies to maybe this electron, for example, it is getting ejected as a secondary electron. Now at this place, when there is no electron, what is there? Hole, right? Hole is the absence of electron. So it means if there is a hole, there are good probability that other electrons which are maybe in the outer shell, they might also like to go there to a more stable position. So what happens that after there is a vacancy here, so the other electrons which are just sitting there, they like to actually come here to more stable position, and when they come here, they will release energy, right? And they will release energy in the form of, when electrons normally jump from high energy level to low energy level, they will release energy in the form of photon or light. Okay, and then what kind of energy or what kind of frequency they will release the photon? It depends on from which energy level to which energy level they are jumping. So in this case, let's say it's from jumping from a higher shell to lower shell, so they will be giving us some photon or energy. And that energy, now think about it, if there is a material which has thousands of atoms, and this phenomenon is happening in all that target material. So, and if you look at the overall spectrum, a lot of X-rays will be generated, a lot of photons will be generated. Okay, and those photons are X-rays. So not always, let's say if I take any material and if I shine with electrons, with low energy, I may not get X-rays from that material. The reason is that for the X-rays, for X-ray generation, you have to use a very specific incident energy for the electrons, so that you can actually eject very specific electrons from inner shell, not only from the outer shell, but it should go inside. It's normally in the 20 to 60 kilowatts energy required to eject to produce X-ray. And it also depends on the material. Normally metals are used as a target, like a copper, tungsten, so those are commonly used materials to produce X-ray. So the point is, yes, you can have then this kind of energy release, and that energy, because of this electron which is coming and filling up, will produce a photon, and that photon is in the form of the X-ray. So let's say if I draw this pattern, let's say I have a pattern, let's put a wavelength on this side, which is lambda, and then on this side we have intensity, for example. If you look at this pattern, how much intensity we are getting at different wavelengths, so this energy which is being released, you will get a peak some places. Okay, then you will have maybe smaller peaks, and then maybe other peak, other place in that way. So this peak, you get it because many electrons from outer shell falls into the vacancies in all those atoms. So that produce because they're coming from a specific orbit, so they will produce very specific energy or intensity at that wavelength. Let's say if this electron is producing 0.1 lambda, okay? So let's say this is 0.1 lambda, this is, let's say, 4 lambda, for example. So at specific lambda or specific frequency, that energy is released, and if that is being released by thousands of atoms, so you will, if you look at the spectrum, you will see that at 0.1 lambda you have a high energy or high photon or high light generation, and that when you use a filter, so you can filter that and use it as an X-ray, and that is actually X-ray. And then in that way you can maybe select another peak which may be lower energy because it's a larger lambda, right? So large lambda means less higher frequency. Large lambda means a lower frequency and less energetic. So it may be soft X-ray, for example. So in that way, you can have a spectrum of different frequencies being generated by your exposure with the electron gun, and then you can use the filters to just select specific one. So in that way, you can have actually electron generation. And now those X-rays, now you can shine it on your wafer with some mask or something, so that you can have a photolithography. But anyways, let's come back. So we have electrons shining on the surface, and when they eject the electron, they become secondary electrons, and now the electrons from the outer shell can come also from the top outer shell to the inner shell to fill in those vacancies, and those are producing their release energy in the form of X-rays. Okay. Now what happens when they release this energy? It can also happen that there is an electron here which was not involved in this one, but when this X-ray energy is released, this electron absorbs that energy. Okay, it absorbs that energy and then it gets out. It's get ejected because of that energy absorption. That can also happen. And when this is ejected because of this X-ray which is being released, then these electrons are called, anyone knows? OJ electrons, okay? And all these electrons are used very commonly for material characterization. OJ secondary electrons and the photoelectrons, so these all electrons are used also during imaging or material characterization. So they are very important. All of them are very important. So let's look at one example. There's one technique is called the X-ray photoelectron spectroscopy, or XPS. You might have heard about it. Anyone who is from chemistry or even from biology, very commonly used method for surface characterization. So when we say X-ray photoelectron spectroscopy, so what maybe we would be doing? So X-ray photoelectron. So in this case, we use X-rays actually to expose the surface of a material. It's kind of opposite. We use X-rays to expose the surface of a material. Like we take X-ray and shine it on some surface, because X-ray is also energetic. They can also kick out the electrons. And when they kick out the electrons, those electrons are called photoelectrons, because you are using a photon source to kick them out, right? So previously when we are using electron gun to kick out electrons, and the electrons which were kicked out were called, what was they called? Secondary electrons, right? In this case, it will be called photoelectrons. And when we look at those photoelectrons, we also look at their energy spectrum and all that, and it can give us a very nice pattern of how much, what kind of electrons are being ejected. And from there, based on that, you can get the information about the composition of a material, whether it's a carbon, nitrogen, whatever. And the paper which I showed you, it has some on the nanopore, thermal shrinking of a nanopore. It also has one pattern where you see the, let me see if I have for you right now. We can look at it together. So for example, this pattern, if you look at the energy which is being released and counts these also, and then see how much we are getting. So a very specific energy we are getting this peak, and another specific energy we are getting that peak. And that peak is is linked with the silicon or oxygen, depends on the location. So let's say if I have this material, if I have this material and if I use a EDS, this is another method to characterize. It's also X-ray based. And what you do is you look at, okay, what kind of photons we are getting from there, okay, and from that you can tell whether it's a silicon or or oxygen. I have actually more complex. Let me show you. Okay, so in this one we use, I think, see, this is more complicated. So we looked at the surface of a chicken egg shell, the chicken egg which we have, and the shell of that. So we were using it for some purpose, and we built very nice features on that of it. This was a raw chicken egg shell, how it looks like. And then after some treatment, it makes in the calcium sulfate crystals, and then also make with the other treatment some nano pattern surface. These features are very, very small, and these are SEM images, and you can see how small you can see with that. So but coming back where we were, so we look at the actually energy and see when there is a one material which is unknown, right? In reality we don't know. When you have let's say if I have, this is an eggshell, okay, maybe I know about it, but when I do some treatment I get this pattern on the surface. How do I know whether this is the same material or different material? So then it's unknown, right? So you are investigating that, and so when you look at now the material composition and see, okay, now after that we have maybe less carbon, we have more oxygen, similar oxygen, but we also now have a sulfur there, which was not before, and then we have calcium, and the calcium is already there. So calcium gives us two peaks at different locations. So basically the sulfur comes into play, and I can tell you that this was a calcium carbonate with some nitrogen, but this was calcium sulfate, and that's why you get a sulfur there. That's what we figured out. And then we also looked at the X-ray crystallography, which is a different thing, but we'll not go into that detail. So but with all these methods, how these energy spectrum looks like, or photon electron looks like, you can actually find out, okay, what material you are looking at. Okay, that's very commonly used methods in material chemistry. So X-ray photoelectron spectroscopy, or XPS, is commonly you shine a surface with the X-ray and then look at the ejected electrons. Those are the photoelectrons, and the energy spectra of the photoelectrons is very specific for different materials. And let's say if you have calcium carbonate, or maybe if you have a hydrogen or something else, so you will get a very different spectra. And based on that, you can characterize if that material, what that material is. It's not an easy task, but you should be able to do that. There is an Auger electron spectroscopy, and it's Auger. It's just the difference is that now you look at the Auger electrons, okay, not the secondary electrons, because some material will give a very distinct pattern in the Auger. So sometimes we have to use more than one technique to find out what that material is. Now there is another issue which comes into picture when we work with the high energetic beams like X-rays, and these X-rays are very penetrating, and they also produce photoelectrons, as we know, right? And if we have a regular photoresist, and if we shine it with the X-rays, so they are too penetrating, they will pass through it all the way, and they will generate a lot of secondary electrons. That's how the regular photoresist is used. So you shine it with some light source, it provides energy, and then a secondary electron generation, and that breaks down the polymer chains, okay, because of heat production and or sometimes it's a chemical reaction. So yeah, secondary electrons are important also for important in the lithography, but on the other way, if you have too much of a secondary electrons, then it will be harder to actually control the exposure. And if the X-rays are too penetrating, which will also not be good, because then your material will be very, very sensitive to the X-ray. And if you look at certain materials which are being used, especially with the X-rays, so look at the material. Let's look at the first EUV, extreme UV, which is lambda 13.4. This is soft X-ray. So gold, this is the penetration depth. In a gold, it can penetrate up till 15 nanometer. Although gold is a very good reflector, okay, but in that high frequency, that light wave can actually X-rays can enter into the gold surface. And when we use a hard X-ray, where 0.45 lambda, a proximal X-ray, then the penetration depth is 170 nanometer. So it's really going deep inside. So it's still not transparent. So let's say if you have a wafer, and if you want to block you want to make a pattern on the mask, okay? So you want to make certain things transparent and other things not transparent based on your features. So the areas which you want to make opaque, you cannot use a chrome anymore, or not even gold. If you have 100 nanometer gold to block the light to pass through, this X-ray will penetrate through it, okay? So it means you will have to use a maybe thicker layer of gold in this case, okay, to block that in a mask. And for example, if you look at even in silicon, it can go about 300 nanometer or 3.3 micron deep inside the silicon. So if you have any doping there, it will disturb the doping. So the PMMA, the extreme UV, the penetration depth is 200 nanometer, and in this case it's 500, like 15 micron. So, and PMMA it has more penetration depth in the hard X-ray, so which is not a good material to be used in a mask, but it may be a good material to use in a photoresist where you can have a good exposure.
What is PMMA?
PMMA is the one polymer, polymethyl methacrylic acid, something like that.
Oh.
It's a polymer. It's used also in a E-beam resist. This is X-ray, but it's used. PMMA is used for E-beam. I know at least that is being used there as a resist. Means that when you have exposure of E-beam, it's a polymer. So it breaks down from that area, and which can be developed like we have a regular photoresist. And PMMA is also present in the form of plastic sheets, so it has a different form. So the regular plastics we see, transparent ones, many of them are PMMA based. So yeah, so different materials can have different penetration depths, and that defines whether you can use it with a certain technology or not. Again, coming back to extreme UV, where you have high penetration depth, typically lambda is 13, as we see it, 13.4. Then the photon energy is about 100 electron volts, which is significantly higher than the band gap of quartz, which is 8 electron volt. So basically, if you use a quad with this one, it will be useless. In a few seconds, your quad would be totally densified, and it will have a lot of defects at different places, and it might melt down if you expose it for a longer period of time. So a quad base, and it means then your optics cannot be also quartz or glass based, so you have to use the reflective optics as we discussed previously. If you go to the proximal X-ray lithography, which is actually hard X-ray or medium energy X-ray from 0.4 to 1 nanometer, or it can be hard X-ray which is less than 0.01 nanometer. So those X-rays are also very penetrating because they are very highly energetic, and but we still use them for we can still use them for the lithography, but the systems are then becomes very expensive. They use a different formula to find out the minimum printable feature with that X-ray. So R is a resolution, K is again a constant, then lambda is a wavelength of light, and G is a mask wafer separation. So if you have a smaller separation between a mask and wafer, it means you can have a better resolution. Or if you use a lambda which is smaller, let's say if instead of using 1 you use 0.4, you can also improve that. It's very similar to the previous equation where we have a W min is equal to K lambda over numerical aperture there, right? In this case, because we are using a different kind of lenses, we don't use the exactly same formula. Then there is another direction that we can take. Instead of X-rays or high energetic beams, we can also work with electron beams, right, or ion beams directly to write it on the surface. And that's where the electron beam lithography and ion beam lithography comes into play. And they are sometimes also used as a projection lithography. You will see to improve the throughput, and we'll also go through soft and imprint lithography, which are different techniques. So let's look at maybe first the electron beam and focus ion beam lithography. So the electron beam lithography is more commonly referred as an E-beam lithography. And in the E-beam, basically you have electron gun where electrons come and elastically actually strikes the other in the photoresist. There would be, so again, there will be not photoresist, it will be E-beam resist. So your electron, you will shining it on the surface, and then they will come and kick some electrons out and transfer energy as a heat, and also they will transfer momentum. So because of that heat and momentum transfer, the photoresist will be at certain areas where it is exposed, it would be disintegrating or broken down into small chains in which you can develop later on. And this is how this equipment looks like. Its first technology was developed around 1960s. And it's a very similar principle how the electron imaging is used, scanning electron microscopy is used. It's actually many systems where we have a scanning electron microscope, we can also do the lithography on the same system. You can do the imaging and lithography at the same time because you need a electron source, you need a chamber, you need a place to put your wafer. So it's very similar, but you just need a different sensor if you want to do the imaging, because you need a sensor to detect secondary electrons in that case. So you can draw a pattern, right? But in writing, when you want to write it, you don't really need that ejector. You just need to control the energy of the electrons which you are putting on the surface, and maybe if they're focused or not focused, so they can define your resolution of the system. So this is how the system looks like. Can you estimate the cost of such a system? By just looking at this equipment, how much do you think it should cost? Millions. Yeah, it's a big range. So give me a shorter range. Okay, they can cost actually even less than $1 million also. Okay, it depends. If you just buy the latest top of the notch from market, then it might be $2 million or something. So it's expensive, and it's just a one equipment, right? You also need to buy a lot of other equipments. So if you really want to do a high resolution lithography, but yeah, but scanning electron microscope, many places have it. We also FAU also have one. I think we have a campus on not on Davie campus. There is another one close to the airport. I don't know what they call it. You know, what's the campus name, which is close to the airport? Dania Beach. I think there is one at Dania Beach. There is one at CM. But I have heard, I never use it, but I have heard that it's not excellent one, but still you can use it. But FIU, University of Miami, they have these equipments. They have SEM, TEM, and E-beam lithography equipment also. In case we want to access it, we can go there and use it after training, and we can pay them like they pay. If you are a faculty there, if you are working for that university, still you have to pay the user's fee. It's a minimal, but still you pay it. So we can pay a similar fee if that's considered internal to us, so we can use that for imaging and analysis. So in a regular E-beam lithography, you actually use a focus ion beam, high energetic 5 to 25, 30 kilo electron volts. You put it, there's a wafer here which you can control the stage, you can move the stage left and right, up and down, and then that focused electron beam actually works as your pen, electron pen, for example, where you can write on the surface. You can generate any pattern in the software which is attached with the electron beam controller. Then whatever pattern you feed it to, it will just start writing accordingly. But it's, as we discussed previously, because it's focusing on a very small area, if you want to print a large features, like large surface area, it will take forever to print that. And that's one of the major limitation with the E-beam and also other high resolution systems, where you cannot really expose a large area very effectively at one time. So, but it is still very useful equipment. It can be used for printing at least some of the features which are nanoscale, and you can print other features with maybe other lithographical techniques, EUV or maybe even X-ray. So ion beam lithography uses a very similar principle. The only difference is in this case we use a gallium or argon ions to actually bombard the surface. And they have sometimes advantages and disadvantages. The ion beam mostly shows a better resolution. Ions are larger. You can think about it, these are whole atoms, right? Not just small electrons. So they are big atoms which are ionized. And when you bombard them on the surface, their effect is actually more localized. Why? Because they cannot really penetrate deeper inside a material because of their size. Yeah, if you really strike them with a high energy, then yeah, you may be able to penetrate them deeper, but if you use a similar energy for electrons can go even more deeper. Why electrons go more deeper? Basically it's a size-based difference. So in electrons, when you push electrons inside or inject electrons inside a material, so what would be stopping electrons to go inside? Its major component is actually electrostatic interaction, because the material where it is going, it also has electrons, right? And this electron which is coming from the outside, the inner electron, similar charge, they will try to push it or stop it. Okay, don't go inside. So, but if you have energy, it will release energy, but it will go to a certain depth. But now in the case of ions, they are larger, they have electrons and protons, both. When they go inside, so you have a electron stopping and also you have a nuclear stopping, because then there are protons also which will try to also stop it because of a proton, and it's a big, so it cannot really go deeper, and you have energy dissipation more localized. So if you use it efficiently, and there are different forms of electrons, we don't have much control just on energy. We cannot control like large electron, there's just one electron. In case of ions, we can use ions which are larger and smaller based on gallium, argon, or maybe other material which you are using as an ion. And in that way, you can have a light ions or heavy ions, and they have different properties based on their penetration depth. The light ions works very similar to the electrons because they're also small size. They can go deeper. Heavy ions go less deep, and but you ended up actually get slightly better resolution if you use the ions. But the principle is very similar. Okay, let's look at some example of a EBL. Is called E-beam lithography, like what we discussed. And let's say if we want to have this nano gap, so these are the electrodes, two electrodes which we have made for some purpose. And we want to have this small gap in there, which I don't know whether you can see it. It's a 4 nanometer gap. How we can have that gap? We cannot do that with the regular lithography. So this one, we use the E-beam can be a good method, electron beam lithography, to actually have that smaller gap. This is another image, E-beam defined metal nano electrodes, and this is a magnified view, and you can see they are very small. I don't see a scale bar there. Let me see in my computer, but this looks to me okay. This whole thing is 200 nanometer, and this one block would be 20 nanometer. So this would be around 20, or maybe I don't know. I can only estimate. It's around 20 nanometer gap between those two, and you have such a nice resolution. When we talk about nanometer, it's not a big thing. It's really, really small. So you really need a very, very super resolution system to achieve that. Okay, and that has been shared with the E-beam lithography, and also with the ion beam. So the paper which I shared with you for the nanobore fabrication and shrinking, in that paper we were using actually ion beam. If you read the paper, to drill holes. In that case, we were not doing the lithography, because ion beam is used for many different purposes. It's also used to etch certain materials. Let's say if you use an ion, a certain material, you focus it and choose a specific energy, you can actually erode certain material or etch away certain material because of the ion bombardment. So they will not penetrate, but you can remove the material. You can also deposit certain material as small area. If you use an ion beam, if you do the whole process in some chemical vapor environment, which can deposit it which can get deposited if you give it enough energy. So then we can actually focus on a small area in the chemical environment, vapor environment. Then that material will be getting deposited very locally in that area, if that is desired for some reason. So yeah, in our case, what we did is first we used actually TMAH to make that kind of a window structure. So let's say this is a wafer, so we open a window, so it goes all the way through deep until we etch the whole wafer through. And on the other side, there was just a thin membrane of silicon dioxide, because the TMAH doesn't have silicon dioxide, so they will stay there. So basically, if you look at the wafer on the top, you can see through it. There will be from that window, which is about 200 or 300 micrometer side. You can see a small dot there that's transparent. Because silicon dioxide, when it's very small, it's very thin, it's transparent, like glass. So once we have that window, then we look under the SEM and find that window. Okay, this is a window, which is where we have a silicon dioxide, which is about 200 nanometer thin. Now we can actually drill something in there, because thin, right? We cannot drill a small hole in a thick wafer. It will be impossible. But when you have a very thin membrane, we can make holes there. And what equipment we can use to really make a small hole, I would go with the E-beam. Electrons normally are not used to drill holes, because they don't provide enough momentum transfer to the other materials. So, but if we use ions, so they can quickly, in few seconds, they can drill a hole inside thin membranes, and that's what we did. So we drill a hole inside a thin membrane and and ended up making that pore, which was about 200 nanometer in diameter, and then later on we reduce it we reduce the size of that with a thermal shrinking, but that's not important right now in this case. But I want to show you some applications that E-beam lithography. So you can find tons of papers where people have used E-beam, thousands of papers, or maybe million paper where people have used the E-beam or ion beam lithography for different applications. There is another variant from the standard E-beam lithography. It's a difficult name. We call it Scalpel. It's a scattering with angular limitation and projection electron beam lithography. Okay, it's a long name. You don't have to memorize it. But what we are trying to achieve with that kind of modification is that we are trying to actually improve the throughput of the E-beam lithography system. As you know, the E-beam lithography and other serial lithographical processes are are suffering because of the throughput issues. Although they give a very good resolution, we cannot really print a large area with that. So one way to go around the problem was, I think it's good and innovative. And if you want to actually read more about any of those technologies, I'm also giving references at certain places, and you can also find by yourself. Because we will be covering a lot of topics, so I'll not be going into much more details. Then it becomes a more maybe e-beam focused course. Not really, because we have to cover a lot of topics. So I will be touching about in some of the topics, and sometime I go deeper where I think it's more important to explain, but sometime I just give you an overview of what options are available out there and how they work. So in this Scalpel case, so what we use is, in a regular e-beam we don't use a mask. But in this case we thought, okay, why not, instead of using a focused electron gun or focused electron beam to small area where we can write. So how about if we can just use electron beam, but not really focused, but full broad electron beam, and then use a mask, like we use the optical mask, right? But what kind of mask we can make with the electron beam? Because if mask is thin, if it's thick, the electrons will not penetrate, right? If it's thin, right? If it's a thick mask, like a thick glass which you have optical, the electrons will not be able to pass through that. But if we have a thin, very thin mask, then maybe all of them will pass through. But how we can make the things which are darker or maybe opaque or transparent to the electron gun? Anything which we see is, for example, this is opaque to me, right, with the two eyes, but it may not be opaque to the X-rays, right? For X-rays, you may be able to see everything what's on the other side. So when we talk about anything is opaque or transparent, we also have to look at, okay, what exactly we mean, at what frequency it is opaque. So in this case, the idea was to use a very thin silicon nitride membrane, which is about 100 nanometer, and on top of that we have 50 nanometer of tungsten and chrome. Okay, so these are opaque areas, so we use chrome there. So the basic idea is, when the electrons will come and shine on the surface, wherever we have a thin silicon nitride membrane, like in this area for example, the electron would scatter. You know, when electrons come and hit the surface, they passes through the material, they will scatter because they will be interacting with the material electrons and all that. Because of that scattering, you will see some scattering of the electron beam here, and then you use apertures or lenses, electromagnetic lenses, to actually focus them in certain areas. So, but you will see some spreading, but less spreading as compared to, or less scattering as compared to the areas which were opaque. Let's say in this case, this square block, whenever electrons will hit that area, you will see more scattering because they are thick, and also you have metals there. So they were scattering more of the electron beam. So when they scatter more, again passing through the aperture, you will still get something on the surface, but it would be of low energy. When you have less scattering because of aperture, you ended up actually getting, you see, that's why the middle line is shown as a more thick and dark, which shows that it's more intense. So it means more energy can pass through because of less scattering. But if there is more scattering, so this aperture, a lot of electron beams part would not be able to pass through this aperture. So only little will pass through because of wider scattering, and you ended up actually getting less electron on this surface where you may have a photoresist, right? So then you have to choose a photoresist which should be sensitive to this kind of electron energy, not with that. It means it should require enough energy before it can resolve a pattern. So by doing it, you can use a mask. You can, with this technique, you can actually improve the throughput of a system. I don't remember on the top of my head what was the resolution, but I believe it should be lesser than the regular e-beam lithography. Okay, I think I have a graph here. Let's look at the graph. So look at this graph. So in this graph, it shows the evolution of electron beam lithography, and if we look at, this is a single pixel, and in a single pixel case we can achieve very high super resolution, right? Very high resolution, but pixel per sheet would be very low, means we cannot print a lot. But then later on we start going towards the mask making and other forms of e-beam lithography, and Scalpel is here where you can achieve a lot of pixels. Like you can, not a single, you can maybe write 10⁻⁷ approximately pixels, like 10⁻⁷ pixels, small areas per shot, means in one exposure. So basically you can expose much larger area, but it will, in this case, again, you cannot really expose a whole wafer. It would be a small area, but large enough than the just 1 pixel. Because if we can expose, let's say 1 millimeter by 1 millimeter, or a few micrometer by a few micrometer, that's a significant improvement. Because previously when you write features on nanoscale, you really expose only nano area. And if we go to, if we can expose a micron scale area, it means we are improving 1,000 times. And if we are improving we can write in millimeter scale, like small scale, it's still very small, and that is 10⁶ times improvement than nanometer scale exposure. And in Scalpel technology, we cannot expose the whole area, because think about when you have a thin wafer, which is you made in a what membrane? Silicon nitride, which is only 100 nanometer thick. So if you have a silicon nitride membrane which is 100 nanometer thick, how you can make a wafer like that, a big wafer? Because it will break very easily. 100 nanometer is very thin. So it has to be small, on a small area. Can you make this kind of a wafer? Yes, we can use maybe TMH. We can take a wafer, right? We can take a wafer. We can deposit silicon nitride on both sides, right? And then we open a window on one side, do TMH. It will etch all the way through the silicon until it reaches on the other side, where you have opening. Like in one example, what we did was 350 micrometer, right? In a previous class. So we can have maybe that kind of opening, 350 by 350 micrometer, but that would be in silicon nitride, which is on the other side. Then you can tilt your wafer up. Now you have a very thin membrane of silicon nitride, which is 350. Then you can use maybe etching, dry etching, right, to remove it to 100 nanometer. That is what is required in this case. And if you want to deposit chrome and make some features with the chrome or tungsten on the surface, you can do the lithography then afterwards. But then when you use that membrane and you put it on another wafer, so that membrane will then act as a mask, and you can expose maybe the 350 by 350 micrometer in one shot, okay, which is large enough as compared to regular e-beam lithography. In a ion projection lithography, again, it's very similar to the Scalpel, because in regular ion lithography, the reason is that we cannot really expose a large area. Again, the same problem. So then we thought about, okay, why not we can also use an ion beam, but more dispersed. And then we use a stencil, which is a mask, like a similar way as is done in the previous case in Scalpel, and we can expose large area. So these are different ways how the ion beam has been used to improve the resolution. The first way is just use the focus ion beam and write it on the surface. This is more typical, more conventional way of doing ion beam lithography. Okay, you have focus ion beam and write it on the surface. Then we can actually also, there's a way to find, you can look more into this paper, but basically you can also design a mask where you have a stencil where their ions will be blocked in certain areas and certain areas will make transparent. Then it becomes similar to what we do in a regular for lithography, right? So in this case, this mask will be opaque in certain areas. Right now, I don't remember on top of my head what materials they use for this purpose, but this is one way that you can improve the throughput. And then there's ion projection lithography, where you also use a mask, but then you use electromagnetic lenses actually to focus that. So you can use the last mask, as we are doing in photolithography also, and then you use a projection, the electromagnetic lenses actually to shrink those ions into a small area. So from large masks to the small area, then in that way you can have a small features, but again with the because you are using a mask, so you can improve the throughput to some extent. Okay, so today we kind of covered a little bit more than what we normally cover, which is fine. Sometimes the lecture need to be a little bit more intense. Now let's talk about briefly about the key paper review thing, which I was mentioning. So I'm giving you 2 weeks now, and to think about a topic, what topic you want to choose as a key paper review. Make sure that you don't get late from this deadline to submit your nomination. When I say nomination, basically you have to find a key paper, any topic. It can be any topic, it's very general. It can be any nano lithography or bio or applications of the devices or features which you made in a nano or in biotechnology or in a sensor development, in a particles development. It can be anything. It can be any topic which we have not covered so far, but you know about it or you are interested in it, you might have read about it, so you can also consider that topic as your key paper. So key paper, many of them will not be latest research. So some of the key papers will be latest ones. Some of the one might be published in 1970, for example. Okay, because if you want to talk about something which is very basic and it may have been invented, let's say take